Good day, I am Oliver Mañgosing and I am here to present problem number 1. This is problem number 1. In this problem, we are given a device which produces chilled air at negative 25 degrees Celsius and 1 bar, and also produces warm air at 75 degrees Celsius and 1 bar, given a supply of compressed air at 25 degrees Celsius and 5 bar. For this problem, I chose a basis of 1 mole of compressed air. And from this, we are required to find the ratio of the chilled air to warm air, and also we are required to find if this device follows the second law of thermodynamics, or in other words, if the entropy generation is greater than or equal to 0. We must first find the number of moles of chilled air and warm air. To do this, we perform an energy balance on the open system at steady state. Afterwards, we assume that we have negligible height and velocity differences between the entrance and exit, and that there is no heat transfer and no work done on the system. Based on our assumption, the energy balance simplifies to this equation. Afterwards, we can expand this expression as follows. Next, we substitute values from the diagram where N chilled is N1 and N warm is 1 minus N1. For this calculation, we can arbitrarily set H compressed is equal to 0. This is possible because what we are only calculating for are enthalpy differences such that the 0 point of the enthalpy is arbitrary. Using this, we have H chilled is equal to H compressed plus delta H from the compressed state to the chilled state. H compressed is equal to 0 and the delta H is equal to Cp times T chilled minus T compressed. Similar to this, we have H warm is equal to H compressed plus the delta H from the compressed state to the warm state. H compressed is 0 and the delta H is Cp T warm minus T compressed. Substituting the previous relations to the energy balance and substituting Cp equals 7 halves R, we get the following equation. Substituting the values, we have R is equal to 8.314 joules per mole Kelvin. Temperature of the chilled air is 248.15 Kelvin. The temperature of the compressed air is 298.15 Kelvin. And the temperature of the warm air is 348.15 Kelvin. Afterwards, we solve for N1, which turns out to be 0.5 mole. We can now compute for the ratio of chilled air to warm air, which is N1 divided by 1 minus N1. The ratio turns out to be 1, such that the device produces equal amounts of chilled air and warm air. To determine if the device follows the second law of thermodynamics, we perform an entropy balance on the steady-state system. Since the device performs adiabatically, Q equals 0, and the equation reduces to this equation. We expand the previous expression and substitute values from the diagram, yielding this equation. Similar to enthalpy, we can arbitrarily set S compressed is equal to 0. We can do this because what we are only calculating for are entropy differences, such that the 0 point of the entropy is arbitrary. Using this, we have S chilled is equal to S compressed plus the delta S from the compressed state to the chilled state. S compressed is equal to 0, and the delta S is equal to Cp ln T chilled over T compressed minus R ln P chilled over P compressed. Similarly, S warm is equal to S compressed plus the delta S from the compressed state to the warm state. S compressed is equal to 0, and the delta S is Cp ln T warm over T compressed minus R ln P warm divided by P compressed. Substituting the previous relations to the entropy balance and substituting the value of Cp, we obtain the following equation. Substituting values and solving for Sg, or the entropy generation, we have the entropy generation is equal to 12.966 joules per Kelvin. Since the entropy generation is greater than 0, This device follows the second law of thermodynamics.
Problem number 2, presented by Lorenz Peter B. Ares. Steam at 6 megapascal and 400 degrees C is flowing in a pipe. Connected to this pipe through a valve is a tank of volume 0.4 cubic meter. This tank initially is at vacuum. The valve is opened, and the tank fills with the steam until the pressure is 6 megapascal, and then the valve is closed. Heat transfer occurs from the tank to the environment in the amount of 95 kilojoules per each kilogram of gas that flows into the tank. The environment is at 25 degrees C. We are given a steam at 6 megapascal and 400 degrees C and a tank in a vacuum, and another pipe that leads to the other reservoir. The volume of the tank is 0.4 cubic meter and thus 95 kilojoule of heat exchange with the surroundings per kilogram of steam in the tank. Initially, the mass inside the tank is 0 kilogram. The temperature of the surrounding is given at 298.15 Kelvin. The valve opens and the steam starts to float into the tank until the pressure of the tank is equal to the steam, which is 6 megapascal. In this part, the final temperature of the tank and the mass of the steam in the tank can be calculated in the later part of the presentation. The valve then closes after the tank's pressure is equal to the steam. A. Determine the final temperature of the steam in the tank immediately after the valve is closed. The first step in this process is to do mass balance. Mass balance is given by this equation. Delta M dot may be written as this term. Since there is no steam that goes out in the process, M out is equal to 0. The mass flow rate in can then be expressed as the change in mass with respect to time, or this term. Multiplying dt in both sides, it results into this. By integration, it shows that the mass inside the control volume is equal to the mass of the steam entering. The next thing to do is to perform an energy balance. The general energy balance is given by this equation. Assuming that there is no change in kinetic energy, potential energy, and no work done, the balance now reduces to this equation. The delta term in the equation can be expressed as the difference between out minus in, hence this equation. Then again, since no steam flows out of the process, the second term cancels out to 0. This leaves us with this equation, and according to our mass balance, the mass of the controlled volume is equal to the mass in, hence this equation. Since m dot and q dot can be expressed as derivatives with respect to time, the equation now changes to this. By multiplying dt in both sides and integration, the energy balance now results into this. Since q1 is equal to 0 and the mass of the control volume initially is equal to 0, it now results to this. By dividing both sides with the mass of the control volume at final states, it results into this final equation. This is the final energy balance equation, which will be used to analyze the system. Using a steam table, the enthalpy at 6 megapascal and 400 degrees C of steam is equal to this. It was mentioned in the problem that the tank exchanges heat with the surroundings at a rate of 95 kilojoules per kilogram of steam. Since the tank gives off heat, the sign is negative. By addition, the internal energy of the tank after the pressure equilibrates with the steam is equal to 3085.1 kilojoules per kilogram. To determine the temperature of the tank when its internal energy is equal to this, we can use a superheated steam table and interpolate values from the given table. Let T be the temperature of the steam when its internal energy is equal to 3085.1 kilojoule per kilogram. Thus, by calculation, the final temperature of the tank is equal to 501.37 degrees C. B. Determine the entropy change of the universe for this process. The total entropy change of the universe is equal to the change of entropy in the steam inlet, the tank, and in the surroundings. Since the inlet steam remained the same throughout the process, hence no entropy change is observed. Thus, it is equal to 0. The entropy change in the tank is given by this equation, where S2 and S1 can be obtained from the steam table and M2 can be calculated. Since the tank is initially in vacuum and has no mass, S1 and M1 is equal to 0. It was calculated before that the temperature of the tank is equal to 501.37 degrees C. The absolute entropy of the superheated steam at this point can be calculated using interpolation of values. Let S2 be the absolute entropy, so by calculation, S2 is equal to 6.885 kilojoules per kilogram Kelvin. The next step for the process is to calculate the mass of steam in the tank. The specific volume in this temperature can be determined by interpolation of values from the steam table. Let V be its specific volume. Hence, the specific volume in this temperature is equal to 56.711 cubic centimeter per gram. Converting the specific volume to the desired units, the specific volume is now 0.0567 cubic meter per kilogram. The mass of steam in the tank can be calculated by dividing the tank volume and the specific volume of the steam. So by substitution of values, The mass of steam in the tank is equal to 7.0532 kg. By substituting all the values obtained from the preceding calculations, the change of entropy in the tank is equal to 48.5676 kilojoules per Kelvin. The next part is to calculate the entropy change in the surroundings. This value can be obtained by dividing the amount of heat exchange and the temperature of the surroundings. Since we were given that the heat exchange occurs at 95 kilojoules per kilogram of steam, multiplying this to the amount of steam in the tank, it gives us a heat value of 670.05 kilojoules. Dividing the obtained Q value with the temperature of the surroundings, it gives us an entropy change of 2.2474 kilojoules per Kelvin. By summing up the entropy change in the inlet, in the tank, and in the surroundings, the entropy change of the universe is equal to 50.815 kilojoules per Kelvin. C. Determine the lost work during this process. The lost work for the process can be calculated by this equation. So by multiplying the entropy change of the universe and the temperature of the surroundings, the work lost in the process is equal to 15,150.49 kilojoules.
Question number 3 of the problem set. A shell and tube heat exchanger is designed to warm air from the environment by condensing steam that is passed through the tubes on the other side. The maximum airflow is 30 kilograms per minute, and the air is inlet at the temperature and pressure of the environment, 285 Kelvin and 1 bar respectively. The steam flows through the stem at a pressure of 10 bar and a flow rate of 3 kilograms per minute. The quality of the steam at the inlet is 0.9 and the exit is 0.2. Calculate the lost work during this process. So we have here a diagram for the problem. So for the solution, first off, we start with the energy balance. And then we assume that there is a negligible kinetic and potential energy, as well as there is no heat transfer and no shaft work supplied, so that ultimately our energy balance will become change of H is equal to 0. But the change of H is just the summation of the enthalpy change of the both streams. So we have here the molar flow rate times the change of enthalpy of the stream 1 plus the mass flow rate of the steam times its change of enthalpy. So for the change of enthalpy of the airstream, we have where H2 minus H1 is equal to the integral of Cp dt from 285 Kelvin to a certain temperature. But we also know that the heat capacity or Cp is just equal to A plus Bt plus dt to the negative 2 times R. And then its constants can be obtained from table C.1 from the book. And then when integrating, we get this equation here. And also, from table F.1, at 10 bar or 1000 kilopascals, we interpolate and then we get the change of enthalpy of the saturated vapor, that is 2776.19 kilojoules per kilogram, and the enthalpy for the saturated liquid, that is 762.58 kilojoules per kilogram. Since we obtained the enthalpy of the saturated vapor and the saturated liquid, we just make use of the definition of the quality of the vapor. That is, it's just the fraction of the vapor at a certain point in the stream. That is, for the inlet or H3, we can get the enthalpy by 0.9 times 2776.19 plus for the liquid 0.1 times 762.58, and then we get 2574.83 kilojoules per kilogram. So for the outlet of the steam stream, H4 is equal to 0.2 times 2776.19 plus the liquid 0.8 times 762.58, and then we get 1165.30 kilojoules per kilogram. So ultimately we can get the change of enthalpy by multiplying H4, multiplying the difference between H4 minus H3 times its mass flow rate. So we get negative 4228.59 kilojoules per minute. And then also we also get the molar flow rate of the airstream, that is the given 30 kilograms per minute times the molar mass. So we get 1034.48 moles per minute. And then substituting all of these values to our equation before, to our previous equation, we ultimately get the T2 or the final temperature of the airstream, that is 423.67 Kelvin. So for the change of entropy of the universe is just equal to the summation of the change of entropy of the both of the two streams. So for the airstream, that is S2 minus S1, it's just equal to the Cp dt over T minus RLN P2 over P1. But since we know that the pressure is just equal to 1 bar, so the second term will be just equal to 0. So if we substitute these values, the equation for Cp, and then integrating, we get this equation here below. So if we substitute all of the values that we obtained before, we ultimately get the change of entropy of the airstream, that is equal to 11.67 joules per mole K. So also from table F.1, we can also get the entropy of the saturated vapor and the entropy of the saturated liquid. That is at 10 bar or 1000 kilopascals. SV is equal to 6.5828 kilojoules per kilogram K, and then SL is equal to 2.1381 kilojoules per kilogram K. And then just like what we did earlier, we can also make use of the quality of the air, uh, or the vapor rather. So ultimately we get the entropy for the inlet, that is 6.1384 kilojoules per kilogram K, and then for the outlet, S4 is equal to 3.0271 kilojoules per kilogram K. Since we have the values for S4 and S3, we can just subtract S4 from S3 to get the change of entropy of the steam, that is negative 9.339 kilojoules per Kelvin per minute. And then since we have all of these values, we can just use the equation that we had earlier, that is the change of entropy of the universe is equal to the summation of the change of entropy of both of the streams. So if we plug in all of the values, we'll get 2732.88 joules per Kelvin per minute. And then finally, calculating for lost work, it's just equal to the temperature of the surroundings times the change of entropy of the universe, and then finally we get 778.87 kilojoules per minute, and that is the lost
Question
work.
number 4 of the problem set.
Consider a piston cylinder assembly containing an ideal gas, initially at 20 bar and 1000 Kelvin. The initial volume is 1.6 liters. The system undergoes a reversible process in which it expands to 1 bar. Take the environment to be at 1 bar and 20 degrees Celsius. Take Cp is equal to 7 halves R. The pressure-volume relationship during this process is given by PV to the power of 1.5 is equal to constant. A. Calculate the work obtained during this process. B. Calculate the useful work that could be obtained by subtracting the energy needed to push back the ambient pressure. C. Calculate the exergy and the ideal work. And letter D. Calculate the lost work. We have here a diagram for the problem. So for letter A, we get the initial volume by using the ideal gas equation. So V1 is equal to RT1 over P1, and then plugging all of the values, we get 0.0042 cubic meters per mole. To get V2, we make use of the pressure-volume relationship stated earlier. So plugging all of these, we get 0.031 cubic meters per mole. And then work is just equal to the integral of P dV. And then making use of the pressure-volume relationship stated earlier, we can substitute P is equal to P1 V1 to the power of 1.5 over V to the power of 1.5, and then ultimately we get this equation here. So integrating the earlier equation, we get 2p1v1 raised to the power of 1.5 multiplied by 1 over v2 raised to the power of zero point 0.5 minus 1 over v1 raised to the power of zero point 0.5. So substituting all of the values, we get negative 10,616.23 joules per mole. And then by multiplying the number of moles, we get the work obtained is equal to negative 42,464.92 joules. So for letter B, first we calculate the V naught, or the volume at the dead state, the point at which the piston has already expanded. So by making use of the ideal gas equation, we get 0.024 cubic meters per mole. And then for V1, we simply just convert the given 1.6 liters into cubic meters and then divide it to the number of moles. So we get 0.0004 cubic meters per mole. And then to get the work needed to push back to the ambient pressure, we just multiply the pressure by the change of volume so that we get negative 0.0236 joules per mole. And then the useful work is just the difference between the work obtained from the process of expansion to the work needed to push back to the ambient pressure, so that we get negative 8,256.23 joules per mole. So for letter C, we first calculate for the exergy, and that is equal to the change of enthalpy minus T naught change of S. But the change of enthalpy is also equal to change of internal energy plus P change of V. And then change of enthalpy is just equal to the CV change of T. So ultimately we get this equation here. And then by plugging in all of the values, we get 12,711.88 joules per mole. And then to calculate for the change of entropy, we make use of this equation CVln T2 over T1 plus RLn V2 over V1. And then by plugging in all of the values, we get negative 10.72 joules per mole per Kelvin. So by plugging in all of the values calculated earlier, we get 9,569.31 joules per mole. And then the ideal work is just the opposite of the exergy. So the ideal work is just negative 9,569.31 joules per mole. To calculate for the lost work, we simply just subtract the ideal work from the useful work. So subtracting both of these values, we get negative 1,313.08 joules per mole.